Okay, so I hope everything went well yesterday with Dr. Coombs. He's a very good organic chemistry professor. So I looked through his slides. He covered a lot of stuff. So we're in good shape to finish this chapter today and hopefully start the second half of chapter 2 today as well. I'm going to finish my slides. I did put up a lecture that I gave during office hours yesterday. So it had my slides. So you kind of had two lectures or two available lectures yesterday. And Dr. Coombs, I didn't get a video from him or the Zoom recording, but his slides are online. So where I had left off last night was with starting to make double and triple bonds using valence bond theory through orbital overlap. And we had ended with ethylene, but what we had done was we had looked at compounds that have single bonds, and single bonds result from head-on orbital overlap. Okay, so what that means would be like if two cars were going to hit in a front-end collision, that would be head-on. Oops, let me get that centered. Okay, so a double bond, though, has two components. It has a head-on overlap component, and it has what we're going to call lateral. So it has two different pieces that come together to make the double bond. Lateral orbital overlap. Okay, and today we're going to look at the triple bond before we move on to molecular orbital theory. A triple bond has three components. It has one head-on orbital overlap, but it's going to have two different lateral overlaps. Okay. So when you have a single bond, the single bond is going to be made from what we'll call a sigma bond. So if you have one head-on overlap, that's a sigma bond. The double bond has a head-on overlap, so it has a sigma bond component, but lateral overlap is called a pi bond. Okay. So in the triple bond, you have one head-on orbital overlap, so you have one sigma bond, two lateral overlaps, so you get two pi bonds. Okay. So what's important if you look at this model, so if you can see this, the blacks are the carbon, the greens are supposed to be hydrogens. Green is typically chlorine, but you wouldn't have been able to see the white hydrogens against this board. So if you look at this molecule and we turn it, the 6 atoms are all in the same plane. Okay, so that means that they're flat. They can be cut apart or split by a flat surface. So the atoms here are, the carbons are sp2 hybridized, which accounts for the trigonal planar geometry at each of the individual carbon atoms, as well as the 120-degree bond angle that would be from green to black to green. So this bond angle is 120 degrees. So when you look at these sigma bonds, so all these bonds between the black and the green are sigma bonds. They are running, or if you drew a line from the nucleus of one atom to the nucleus of the other atom, this bond would fall right on that line. That's called the internuclear axis. Okay, so sigma bonds are held tightly between two nuclei. But if you turn now to the side, you can see these two components where my fingers are. These are the result of the lateral overlap from a p orbital on each one of these 2 carbon atoms, and it's above and below the plane of the molecule. Okay, so if I turn it, all the atoms are in one plane, but then the pi bond component is above and below. So you need overlap above and below to make 1 pi bond. Are there any questions before we make the triple bond in acetylene and account for both of those 2 pi bonds?
Yes. Are you going to cover the Vesper theory today?
This is Vesper theory.
Oh, okay.
So when you have, so Vesper is a way to account for these geometries. So for example, like if you look at this molecule, this is methane, so a carbon with 4 hydrogens. Okay, so it's not flat. It's not like a plus sign. So what Vesper essentially is telling you is that the molecule is going to orient itself in 3 dimensions so that each one of these pairs of electrons in the bonds have as much room as possible, because the electrons in this bond are negative and they're going to repel the electrons in this bond, as well as the electrons in this bond and this bond. So if you try to make the bonds closer, then you're going to see an increase in repulsion. So it's a balancing of forces. So you have to give each thing as much room, each electron pair as much room as possible. And so that idea of allowing for the spread into 3 dimensions, that's Vesper. That's all it is in a nutshell. And then the result of it are these shapes. So the most efficient way to organize 4 things around a central atom is to assume the shape of a tetrahedral. And that reduces the repulsions between the bonding pairs in each of the 4 bonds. Does that make sense, Hannah?
Yes, thank you. That made a lot of sense.
Okay, good. Okay. Are there any other questions about where we are right now? Okay, so the last thing we'll do is account for that triple bond in a simple molecule. And so the example we're going to use is acetylene. Okay, and acetylene has 2 carbons, 2 hydrogens, like this. Okay. So again, if you were able to watch the video I did yesterday of the beginnings of hybridization, some of this will make some sense. Some of it I might have to repeat. That's okay. So I have this carbon. I'm just going to, that's not an electron. It's the blue dot is just to distinguish the left-hand carbon from the right-hand carbon. Okay. But when you look at these 2 carbon atoms, they're in identical environments. So this carbon atom that has the blue dot is bonded to a hydrogen and then triple bonded to a carbon. The red carbon is triple bonded to a carbon and single bonded to a hydrogen. So the reason it's important to discuss that is that if we hybridize for the blue carbon, it's going to be the same as what we would do if we hybridize, or when we would hybridize the red carbon. So we're kind of doing both carbons at the same time, only it would be an individual activity for blue carbon versus red carbon. Okay, so the way that I like to do that, I'm going to show you the simplest way, and then I'll show you the diagram with the electron configurations. But the first thing that you do is you're going to count and find the magic number. Okay, and what the magic number is the number of regions around the central atom or an inside atom where you find electrons. So you don't hybridize outside atoms ever. It's only inside atoms where this makes some sense. So if we look at the carbon with the blue dot, it has one set of electrons in this region, 3 sets of electrons in this region. But it doesn't matter how many electrons are in the region, it just matters that there are electrons in the region. So this is one region, this is the second region. Okay, so even though there's more electrons in there, it still just counts as a single electron domain. So our magic number for this compound is going to be 2. Okay. Why that's important is that to identify your hybridization, you have to do a simple math problem. Okay, so what you're trying to do is find s raised to the first power, p raised to x, and then 1 plus x has to equal that magic number of 2. Okay. So this is a pretty simple subtraction, and x would be equal to 1. All right, and what that means is that each one of these carbon atoms ends up sp hybridized. I think my cat's being bad. Oh, hang on. Sorry. So the sp hybridization accounts for linear geometry. Okay, so acetylene is in a line. Okay. What your magic number is telling you is the number of hybrid orbitals you've made. So there are 2 different sp hybrid orbitals on each of the carbon atoms. Okay. Now, what that means in terms of making the bond angle, or the pi bonds, excuse me, is what happens if you would look at the electron configurations. Okay. So before you hybridize, what you're looking at are atomic orbitals on the carbon atom. Okay, so you would have your 1s electrons down here, 2s, and 2p. The reason why this 1 is here is because there's only one s orbital in any energy level. So this is telling you the number of the kind of orbital that you use when you hybridize. Okay, but you have your magic number, and you put a box around that many valence orbitals. So these are core, so we're going to ignore the 1s orbitals. Okay. And we're going to put a box around 2 of the 4 valence orbitals. So those are the ones that are going to be hybridized. Okay. These other 2 here, these we're going to ignore or leave alone. Okay, so we don't have to use those. All right, I'm going to have to erase this wording in order to get the rest of this in. Okay, so this is the part that's supported by math that you never do. You don't really solve this. Is you're going to mix. And what that means is you're going to add the s orbital to the p orbital. Okay. Oops, my cat is coming to say hi. Okay, so this is the new electron configuration for the hybridized atom. The 1s electrons are the same. so that you don't ever do anything to the core. Okay. If you use 2 orbitals in the box, you make 2 hybrid orbitals. Okay, and these are your 2 different sp hybrids. Okay, now slightly higher in energy, but not very much higher in energy. Those are the 2p over here that you left alone, that weren't included in hybridization. Okay, this energy gap here, delta E, is very small. So when you put these 4 valence electrons in these orbitals, they get spaced out in this way. Okay. When you have electrons that are in the same orbital, and they're of opposite charges, or sorry, opposite spins, this arrangement costs some energy for the atom, and it's called the spin pair energy. So in order for these electrons to distribute in this way, the spin pairing energy here is greater than the energy difference between the orbitals. So it's cheaper energetically to promote the electrons. So you end up with 4 electrons, 2 in hybrid orbitals, 2 in atomic orbitals. Okay. So sp hybrids are made from a circle and a peanut, and they end up looking sort of like this, like a fat little fish. Okay. The electron is most likely going to be found inside the large lobe of that orbital to give it as much space as possible. Okay. So if we draw what this would look like from the perspective of those 2 carbon atoms. So I'm just going to draw a blue circle for one carbon and the red circle for the other carbon. Okay. So the lobe that's important is that big fat one. Okay. So the blue orbital, or the blue carbon, has a fat lobe going in this direction. The red has a fat orbital going in this direction. And there is your head-on overlap, and that's the sigma bond component of this triple bond. Okay. All single bonds are sigma bonds, so the second sp hybrid here overlaps with the hydrogen 1s orbital, and you have a bond. Okay. And then the same thing happens over here on this side. Okay, and anywhere where you have those dark black connections, those are sigma bonds. So if you look at this molecule, you would say 1 sigma bond, a second, a third. So 3 sigma bonds, and they're on a line between all the nuclei. Okay. Now what we have to do is we have to say, well, what happens to these? Okay. I'm going to try to use orange, although I don't know how well it's going to show up on this screen. So remember, p atomic orbitals are perpendicular to one another. So on the green atom, you have a p lobe up and a p lobe down. That's parallel to a p lobe up and a p lobe down on the red atom. Okay. The top of this p orbital can't head-on overlap with the top of this p orbital. That's geometrically impossible. Okay, but they can tip. So they overlap to the side, top and bottom. That's 1 pi bond. So you have to do the top lobes and the bottom lobes. Okay. All right, I'm going to use green for the other one. So that was one of these 2. The second one is going to be coming out in the front and going in the back, parallel to coming out in the front, going in the back. And then these lobes overlap. Okay, so it ends up looking like a corn dog. So this is the stick The sigma bonds are the stick. And then all around the hot dog, you have cornbread. So you have pi electron density, or you have a pi bond top and bottom, front and back, and it just becomes like a smear all the way around the line of the molecule as the pi bond set. So there's 2 pi bonds. Okay. Are there any questions about that before we move on into molecular orbital theory?
I have a question.
Sure thing, Andrew.
So on the right-hand portion of the screen, like you have we'll call like the energy levels.
Yeah.
So why does that not violate one of the rules where, like, in order to go to the next level, like the SP would have to be 1 spin up and 1 spin down, or?
Yeah. So that, like right over here. Like you have to, the Aufbau principle tells you that you need to fill low energy levels before you fill higher energy levels. Okay, I'm going to just make this much bigger. I'm going to take this stuff over here off and redraw that. Okay, so, okay, here's 1s, really low in energy. Okay, and then a little higher in energy are the SP sets. Okay, so this you would say is large. This is a large difference in energy. Okay, the 2p orbitals are like right here. So that this difference is very small. Okay. So if you have, when you have a choice, you have to ask yourself, okay, so we have to follow the Aufbau principle. So we would go 1, 2. Okay, now we have to figure out what's going to happen next. So you have 2 possibilities. The first is that the atom will pay what's called the spin pair energy and put the electrons in the sp orbitals. Okay, that's one option. The second option is to promote the electrons and put the electrons in the 2p orbitals. Okay, so we're going to say that this energy is spin pair, ESP, and this is going to be EP. Okay, so the energy required to spin pair or the energy required to promote. Okay, if the energy to spin pair is greater than the energy to promote, the cheapest option is to promote. Okay, so it's like if you have 2 choices to buy one item. So let's say you go to the store and you want to buy a shirt. The same shirt will either cost you $20 or it'll cost you $10. Same shirt. You're going to pick the cheaper option. Why would you pay more money to get an identical product, essentially? So the atom is the same way. It's going to choose the lowest energy option. And for this particular situation, it's going to cost less energy to promote to the 2p orbitals than it is to spin pair. That's why they get moved up.
Okay, makes sense.
Okay.
Thanks.
Yep. Any other questions? Okay, so we're going to move on into molecular orbital theory. Okay. Right. And what we're going to do is we've already looked at orbital overlap for the formation of hydrogen, H2. So what we're going to do here is we're going to use molecular orbital theory to explain the H2 molecule. Okay, now everything that valence bond theory tells you has to be supported by molecular orbital theory because it's a more advanced theory. So it's like comparing walking to running. Okay, once you know how to walk, then you can learn how to run. Most people don't learn how to run first and then go back to learn how to walk. Okay, so it's a progression from an easier theory to a more difficult theory. Okay, so we're going to look at H2, but anything larger than H2, you would need a computer. Okay, so if you understand what I'm trying to get across with H2, then the rest of it, you're just going to look at little bits and pieces of molecular orbital theory. When we use molecular orbital theory, we have to add and we have to subtract orbitals. So hydrogen has s orbitals. So we're going to look at what happens when we add orbitals, so blue plus blue, and we're going to look at what happens when we subtract orbitals. Now, there's two ways to write subtraction. You can either write blue minus blue, which is the same as blue plus red. Okay, so I'm going to use this one and this one because it makes more sense to me. Okay, so those are the combinations I'm going to look at. What happens when I add wave functions, what happens when I subtract wave functions. Before we go to that, let me just show you a diagram that might help with why I'm using it this way. So, and then I'll erase this. So let's say that the x-axis here is sea level. Okay, and this is 0. And then we have positive values of height and we have negative values of height. Okay, and we can just pretend this is at Wrightsville Beach and a wave comes in. So when a wave comes in, waves have sort of a sinusoidal property. So the wave comes up, down, up, like that. So relative to sea level, this would be a positive part of a wave. This would be a negative part of the wave. Okay. This point right here in the middle, that's called a node. That's where you have no wave. So you have a wave and a positive portion of a wave, the negative, and these are algebraic. They're not charges. So the algebraic solution, which is positive, the algebraic solution, which is negative. The positive solution, the negative solution. Okay, so that's why we're doing it like this. Instead of saying positive minus positive, we're going to say positive plus negative. And that's what we're doing over here. But it's still a subtraction. Okay, so when we look at these, we have to add and subtract our orbitals. Okay, are there questions about that before I erase my sea level diagram? Okay, so when you draw a molecular orbital diagram, you're going to have a y-axis of energy. And for these small things like the hydrogen atom, we're going to put one hydrogen atom on the right, that's the left, and one on the right. And then we're going to draw the molecular orbital diagram in the middle. Okay, so those two lines represent the energy of the 1s atomic orbital for each of the two hydrogen atoms. This is atomic. This is atomic. Okay, and each one of those has an electron in there, and we're going to have one spin up and one spin down because it'll make it easier for when we put them into the same, when we make our molecular orbitals. Okay, so what we're going to do is we're going to add them together, and put a line down here. So these in the middle are the molecular orbitals. In the middle. So one is lower in energy, one is higher in energy. Oops, I want them to be lined up. Okay. So for molecular orbital diagrams, what you do is you count the number of atoms involved. Okay. For the purposes of what you're going to do. Okay, the number of atoms is going to be equal to the number of atomic orbitals, which is going to be equal to the number of molecular orbitals you build. Okay, so we have 2 atoms, 2 atomic orbitals, and we make 2 molecular orbitals. Okay. Right. This low energy orbital, this is called a bonding orbital. Okay. Bonding molecular orbitals contribute to the formation of a bond. The high energy orbital is called an anti-bonding orbital. Anti-bonding molecular orbitals take away from bonding. So we have 2 atoms, 2 atomic orbitals. We make 2 molecular orbitals, one low, one high. The low energy orbital is bonding. The high energy orbital is anti-bonding. These are just wave functions. Okay, so all orbitals are mathematically described as waves. So the symbol for a wave is a psi, which is like a little fancy Y. So we'll just say that this is wave 1, wave function 1, and this is wave function 2. Okay. Now, when we put the, now we have to deal with the electrons. So you go back, you say, how many electrons have to fill this diagram? Okay. So there's only 2 electrons, 1 from each of the hydrogens. And so we follow the Aufbau principle and Hund's rule, and we go to the lowest energy orbital first. And by Pauli's exclusion principle, we spin pair them like that. Okay, so now the spin pairing energy is lower than this energy gap. So you spin pair down here. Okay. Now you could say, well, what does the shape of this orbital look like? If you add a circle to a circle, you're going to get an oval. Okay. Up here, if you have a positive orbital and you add it to a negative orbital, you're going to end up with a positive side and a negative, a positive side and a negative side, and they're going to be split in half. There's going to be a gap. Okay, the gap is called a node. Okay, so the more nodes you have, this has 0 nodes, this has 1 node. The more nodes you have, the higher in energy the molecular orbital is. Okay. All right, the last thing that, in terms of terminology, that we have to do is these 2 orbitals are spectroscopically important. So if you have a large molecule, you're going to have a lot of molecular orbitals, but the top 2, the highest orbital with electrons and then the lowest orbital without electrons, those are called the frontier molecular orbitals. This one down here has electrons in it, so it's called the highest occupied molecular orbital. So we call it the HOMO. Okay. This one up here is the lowest unoccupied molecular orbital, and we call it the LUMO. Okay. The space between them is called the HOMO-LUMO gap. Okay. Right. The last thing is this energy difference right here from the atoms on their own to the formation of the bond. This difference in energy is the bond energy or the bond strength. Are there any questions about this diagram? There's a lot of information on it, but hopefully it's not terribly overwhelming. And sometimes it just takes a little while to sit. You might have to think about it and ask questions over the weekend or on Tuesday. Okay. Can we move on to show the similarities between the valence bond theory and molecular bond theory for the formation of a pi bond? Okay, I'm going to assume that's a yes. Okay, so if you have the slides available, we're on a slide that says in red at the top, do the theories parallel one another in any way? Okay, and so what this is doing is it's looking at this compound, which is acetylene. No, sorry, I lied, ethylene. Okay, and all we're looking at is the pi bond, nothing else. The pi bond only. Okay, so your first theory was valence bond theory. Okay, and what we said, so here's a carbon atom and here's a carbon atom, these two, and all we're doing is making the pi bond. Okay, so valence bond theory says in order to make the pi bond, you have to have parallel p orbitals that overlap on the top and on the bottom. Okay, so we're going to add the orbitals together. This is p plus p. Okay. What molecular orbital tells you is that you're going to have one carbon, 2p orbital, and then a second carbon, 2p orbital. Okay. I'm going to draw the pictures down here. We're going to add the orbitals together. And for the low energy orbital. And then we're going to subtract or add the opposite to make the higher energy orbital. Okay. We have two atoms, two orbitals, two molecular orbitals. Then we fill the molecular orbitals with the correct number of electrons. There happens to be two, one up, one down. Okay, so this bonding molecular orbital looks exactly the same as this lateral overlap pi bond from valence bond theory. Okay, they end up identical. So whatever you get from valence bond theory, you have to also get from molecular orbital theory. And this is like the most complicated way that you might see something like this. You might have more atoms involved, but it's going to be a question of, can you tell here that these wouldn't add and you'd have a node? These would add and you would have like a red thing on the top, a red oval, and then a blue oval like that. This is what the bonding molecular orbital would look like, this one down here. So this would be bonding, this would be anti-bonding, and anti-bonding would be empty. Okay. Are there any questions about that before we move on into sort of a summary and intermolecular forces?
I have a quick question.
Sure.
How do we know that the top doesn't add?
Well, you have to, in molecular orbital theory, you're required to add and subtract. So when you draw a p orbital, the colors represent the algebraic signs. So this would be like saying, let me draw it over here. You have this, and the reason why they're different colors is it's like, you know how when you do the quadratic equation, you get a positive answer and a negative answer, usually, or you get two different answers? That's what this is telling you. You get two different answers, but one is positive and one is negative. So if you have them lined up parallel, they're going to add together. If you line them up opposite, they're going to essentially subtract. But it's easier to draw it, I think, this way than have red, blue minus red, blue. So this is like saying +5 plus -5. So the combination or the overlap would be 0. And the same thing down here, but over here, +5 plus +5, that's going to be, you're going to get a non-zero answer.
Awesome. Thank you so much.
Yep, no problem. Any other questions?
If you have to do both, then how do you know whether to use the anti-bonding or the bonding in your answer?
Well, the electrons are always going to go into the lower energy molecular orbitals. Okay, so let's take a look at a bigger molecule. Okay, so let's take a look at this one. Okay, so you're really responsible for molecular orbital diagrams that involve pi bonds. Okay, so what you're going to do, you're going to start by saying, how many carbon atoms participate in pi bonds? Okay, and you just literally look at the diagram and you'd say, well, this carbon is participating in a pi bond. This carbon is participating in a pi bond. So is this one. So is this one. Okay, so that means you have 4 atoms that are participating. Okay. To draw your molecular orbital diagrams, what you're going to say is 4 atoms is going to require 4 p orbitals, and that's going to make 4 molecular orbitals. So it's another example of having a magic number. Okay. So then what you would draw then is 4 lines for the molecular orbitals. 1, 2, 3, 4. Okay, now when you have more than two, the naming becomes a little bit more challenging, so you won't have to do that. So we'll just say, well, this is going to be wave 1, wave 2, wave 3, wave 4. Okay. And then what you do is you go and you count the number of pi electrons. So how many electrons are in the pi bonds? There's 2 in this pi bond. Each bond has 2 electrons. So there's a sigma and a pi. So of these 4 electrons, 2 are sigma bond electrons, 2 are pi bond electrons. So you have 2 here and 2 here for a total of 4 electrons. You always start low and work your way high. So you would say 1, 2, 3, 4. So in this case, this is your HOMO, and this is your LUMO. Okay, now if you say, well, what are they going to look like? Okay, so the number of, if you label them 1, 2, 3, 4, the number of nodes starts at 0 and goes up by 1 each time. So this would have 0 nodes, 1 node, 2 nodes, 3 nodes. Now it takes some practice to figure out how that would look in terms of lining up the p orbitals, but 0 lobes is always having these parallel. Okay, so you would get a positive, they would add up across the top and they would add up across the bottom. One node is going to look like this. Where they added here and here, here and here. But where the colors aren't lining up right, that's the node. So here's the one node. Okay. In the third, they're going to be up, down, down, up. They're going to be overlapping here and here. Okay. And then the fourth one, they would have to alternate every time. Now, one thing you have to remember is, like, because we're doing online exams, you're not going to have to draw. Okay, so if you saw a picture that looked like this, and then you saw a picture that looked like this, and you were asked which is the lower energy orbital, A or B, you would say A, because this orbital combination has fewer nodes than this combination. This combination has 3 nodes or 3 breaks between the orbitals. This has 0 nodes, 0 breaks between the orbitals. Does that make more sense?
Yes.
Okay. Okay. You can also do this with lone pairs of electrons. So this is actually I'm just gonna erase part of this. Actually, forget it. I'm not going to forget it from the example, but trying to reuse what I've drawn is driving me crazy. Like that. Okay. So you have a pi bond and you have a lone pair of electrons. Okay, now this is getting a little bit ahead because resonance is in the next bit, and molecular orbital diagrams explain resonance. But what you would end up with is you would have 3 carbon atoms participating in stabilizing these 2 electrons. And this might have to wait until after resonance in these 2. But did you get what were there questions about the last diagram with the 2 pi bonds? I shouldn't have erased it so fast. I was just getting in a hurry. Okay.
Did we have a question like that on the test? You said it would just be more provided the image and then we would.
Yeah, because you can't draw, I mean, there's no way for us to have you draw the image. The problem or the difference on the exam, when we've asked those questions, they're like in black and white. So an example would be like, this is just an extension of the last thing we did. Okay. And so then you're going to say, like, we could say questions like, what is the molecular orbital diagram? Okay. So in this case, you have 6 carbons that are participating in pi bonds, which means you have to end up with 6 molecular orbitals. There's 2 electrons, 2 electrons, 2 electrons, so 6 electrons in pi bonds. Okay, so that would be the molecular orbital diagram for this. Okay, so maybe this is option A, but option B might just be like this. Okay, now the thing about orbitals, it's kind of like having a guest bedroom in your house. Just because it's not occupied doesn't mean it's not real. So these molecular orbitals that are not used to hold any electrons still exist. And so you have to show them as being present. This is wrong. This is saying you just get 3 molecular orbitals from this image, and that's not what you get. You actually get 6, but only 3 have electrons in there. In terms of the pictures, it could be in color now that we have to do it online. If you saw, we've done things in the past where it's like, and it would likely be more than 2, but this is just a way to get it done. Which of those 2 molecular orbitals, A or B, is the lower energy orbital? And so you would pick B because it doesn't have any nodes. A node is going to occur when you're trying to add opposite signs of the wave functions. And so a node means that you have no electron probability. So you're not going to find an electron there. And this is a little bit tricky because at this point then, a lot of organic chemistry is going to make sense if you think about electrons as particles. But there are cases where you have to consider that the electrons are waves. So when you have a wave like on the water, the wave exists here. The wave exists here, but it doesn't exist at the crossover point. So when you think about that in terms of the electron as a particle, it doesn't make sense. So a particle can be here, that same particle can move here, but it can't cross through the midpoint. So there are times where it's going to be easier to think about the electrons as particles, and other times electrons as waves. And in this idea, it's going to be easier to think about them as waves. It can be here, it can be here, but it can't be in the middle. And that makes perfect sense with a water wave. You can have a positive part of the wave, a negative part of the wave, and a portion where there's literally no wave. You're still at sea level. Any other questions about that?
So does molecular orbital theory only go for the pi bonds, only show the pi bonds?
It works, well, you can draw a molecular orbital diagram for an entire molecule, including all the sigma bonds. But it's not trivial. So, and like, I don't want to like be overwhelming. So, let's see. I'm just gonna. I'm not gonna do the whole thing because, like I said, you'll leave this session and be like, I'm tired of her talking. Okay, so nitrogen. Oh, so when you have N2, let's see, 6, 7, like this. Okay, on both sides. So this is one nitrogen, and then you'd have another nitrogen. So down here, you would have the 1s from one nitrogen and the 1s from another nitrogen. They'd add. And they'd subtract. Then you would have the 2s. They'd add and they'd subtract. And then you would have the 2p. And they add and they subtract. So it gets really confusing. Like this is a lot. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atomic orbitals. So then you're going to have to make 1, 2, 3, 4, 5, 6, 7, 8. I've got too many. 9, 10. Oh, I must have counted that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 molecular orbitals. Then you have to worry about whether or not like this molecular orbital is higher or lower in energy than this molecular orbital. So it gets, even though nitrogen is a small compound, the molecular orbital theory gets confusing very fast. So the things you need to be able to do with molecular orbital theory, I would love it if you could, on your own, draw the molecular orbital diagram for something small like hydrogen, and hydrogen only, H2. Then we're going to, now you know, we've just covered the molecular orbital diagrams for compounds with pi bonds. And we're going to do more of that when we talk about resonance. But you won't have to do a full molecular orbital diagram or say if one is correct for an entire molecule, considering all of the overlaps from the 1s orbitals all the way up to whatever else is used. But there are some images in your book where they show you some very complicated molecular orbital pictures, but if it doesn't make sense and you haven't seen it in the lecture, that would be something that you can just say is beyond what you would have to know how to do. Did that answer your question?
Yeah, thank you.
Yep. Okay. Any other questions? And we will practice this more in resonance, which we'll hopefully touch on today, but otherwise we will move on into that on Monday as well. And I'm almost always behind the calendar, so don't panic. Okay.
Monday with holiday?
Oh, no, we don't have class Monday. Tuesday. Yeah, we'll do it more on Tuesday when we get in there. Okay, so the next slide is sort of just like, it's showing you the geometries. So some of this stuff we've gone over. So if you have a carbon that has two regions like that, it's going to be linear and sp hybridized. 3 is going to be trigonal planar. SP2, and then 4 tetrahedral SP3. Okay. So what I would like, I'm going to draw this, there's a molecule on that slide if you happen to have the slide in front of you. So I'm going to copy it here. Okay, and what I'd like for you to do is take a few minutes, and I want you to identify the hybridization at each carbon. So this carbon may have a different hybridization than this carbon, which might have a different hybridization at this carbon. So I just want you to write next to each carbon, whether it's SP, SP2, or SP3. He's just tired. Whatever. So, okay. All right. So again, you're going to look at each atom in the molecule independently from the others for hybridization. So this carbon has 4 things, so it's sp3. This carbon has 4 things around it, sp3. This carbon only has 3, so it's sp2. This carbon is also sp2. This carbon is sp3. This and this one are sp. Okay. So when you talk about the geometry of a molecule, you could be talking about the geometry of the whole molecule or the geometry just at a specific carbon. So this carbon is tetrahedral. This carbon is tetrahedral. But this carbon is trigonal planar. So there's a planar part of this molecule, some tetrahedral components, and then a linear component. The last thing of just general information is if you have a set of bonds between similar atoms. So a carbon to carbon single versus a carbon to carbon double, carbon to triple. If you go in this direction, the bonds get shorter. And as you go in that direction, the bonds get stronger. Okay. The reason the bonds get shorter is because when you have a carbon-carbon to single bond, you're using sp3 hybrid orbitals to make the sigma bond. And they're kind of long and skinny, sort of like more like the s orbital, or sorry, the p orbital. sp2 carbons that have a pi bond, that hybrid orbital is a little bit shorter and a little fatter. So the bond is going to be smaller. And then the same is going to be true for the triple bond. It's even smaller and even fatter. So the bonds get shorter and the bonds get stronger, but it's not linear. So if this is like 360, 370. This isn't 2 times 370. It's greater than 370, but not a double, not just like 2 times, and this isn't 3 times. They just get stronger. Okay. All right. Are we ready to move into talking about polar and nonpolar bonds, overall polarity, and intermolecular forces? Okay, sounds like it. Okay, so the first slide that you see is just kind of a compilation of different images to help describe the bonds. But now we're talking about covalent bonds. And these are going to be when 2 non-metal atoms share valence electrons. Okay. Now sharing can be done in 2 ways. So it's sharing is kind of like playing tug of war. You can evenly share, or you can unevenly share. Okay. When you evenly share, those are going to be nonpolar bonds. Nonpolar covalent bonds. Unevenly shared are going to be polar covalent bonds. Okay. Nonpolar bonds occur when you have twins. So that means like the nitrogen bonded to the nitrogen, a chlorine bonded to a chlorine, a fluorine bonded to a fluorine, 2 like atoms in a bond. Nonpolar bonds also occur when carbon bonds to hydrogen. Okay. Polar bonds are any other combination of nonmetals. So what we're going to look at is this idea of electronegativity, and then what happens when you have molecular geometry considerations to make. Okay. So I'm going to erase this top part so we can keep this last part down there. Okay. And if you move to the next slide, you should see some colored diagrams. And what we have, is we have a chlorine bonded to a chlorine. And for the polar bond, we have a hydrogen bonded to a chlorine. Okay. Now halogens always have lone pairs. So the tug of war is between these electrons in this bond and these electrons in this bond. Okay. So when you have 2 atoms that are identical, they're equally going to pull on the electrons in this bond. Okay. So this would be a case where these 2 electrons are going to be evenly shared. Okay. On this side, with the hydrogen and the chlorine, chlorine has a greater electronegativity than hydrogen does. I'm going to take this part off. Okay. So electronegativity is a measure of how strongly can an atom pull on shared electrons in a bond. Okay. If we draw a very, very rough periodic table, electronegativity increases up a group and from left to right across the period. Okay, so fluorine is the most electronegative atom. The closer two things are located on the periodic table, the less polar the bond is. So if you look across the second period, you have boron, carbon, nitrogen, oxygen, fluorine. Okay. A carbon to fluorine bond is going to be more polar than an oxygen to fluorine bond because the carbon and the fluorine are spaced farther apart on the periodic table. So there's a greater difference in their electronegativity. Okay. So of these two atoms, the chlorine is more electronegative than the hydrogen. So the chlorine is going to win the tug of war. But hydrogen isn't just going to let go. So it's still holding on, but the two electrons in this bond spend more time on the chlorine side. So we indicate that by using what's called a dipole arrow. So you put a plus sign on the end of your arrow, and then you point the arrow towards the atom with the higher electronegativity. Since there's more electron density on the chlorine side, because these two electrons are spending more time over here, you would say this is the partially negative side, and you use a little delta minus. The hydrogen side becomes a little bit positive. These aren't full charges, they're partial charges. It's not like making an ion. An ion would be a full charge. Are there any questions about that before we look at a larger molecule? Because this is just a linear molecule. So when you have something that's linear, the bond dipole and the molecule dipole are exactly the same. But once you get a larger scale molecule, then you have to consider the shape of the molecule in order to discuss polarity. Okay, so these bond dipoles, these are vectors, not scalars, so they have direction and magnitude. So when you add vectors together, you have to consider the geometric arrangement around a central atom. Okay. So if we look at a little bit bigger molecule, we're going to look at chloromethane. Which has a formula CH3Cl. Okay. The carbon is the central atom, and it has four things around it, so it's a tetrahedral sp3 hybridized carbon. So the chlorine, the carbon, and this hydrogen on this side are all in a plane. This hydrogen on the dash is coming to you. This hydrogen on the wedge, oh sorry, this is a wedge. The wedge is coming to you, the dash is going behind you. Okay. Carbon to hydrogen bonds are all nonpolar, but carbon to chlorine bonds are polar, okay, in the direction of the chlorine. So your bond dipole would look like this. And this chlorine would be a little bit negative, and the carbon would be a little bit positive. Okay. In this case, there are no other dipoles present. Okay. So even though these bonds down here are polar, nonpolar, the whole molecule is going to be polar because of the presence of the chlorine atom. Okay. The molecular polarity, so whether or not your molecule is polar, affects how the molecule interacts with its neighbors. And how it interacts with its neighbors, those are the intermolecular forces. Okay. So when you have a large organic molecule, if it has oxygens and nitrogens, sulfurs, halogens, it's most likely going to be polar. It's only when you have a single atom in the center and you can have even or uneven distribution of these bond dipoles do you see the bond dipoles cancel. Okay. Are there questions about molecular polarity before we look at intermolecular forces? Okay. So if you have a sample, you can have that sample in the gas state, the liquid state, and the solid state. Okay. As you go in this direction, you see an increase in the strength of the intermolecular forces. Okay. The kinetic molecular theory that we use to describe gases actually indicates that ideal gases don't have any intermolecular forces. Real gases do, but they're just pretty minimal. So you also have a temperature effect here. So these are going to obviously be low temperature samples, which means you have very little molecular motion. So if the molecules aren't moving very fast, they have time to interact with their neighbors and develop the intermolecular forces required to keep the sample in the solid state. As you warm the sample up a little bit, then you're starting to disrupt intermolecular forces, and the molecules have more freedom of motion and they can assume the liquid state. And then if you warm it up even hotter, then you have such high molecular motion that the samples of the material don't have time to develop intermolecular forces with neighbors because they're just passing by each other so very fast. Okay, so there are three types of intermolecular forces that we have to discuss. The first is called London dispersion forces. And these are in all covalent compounds, regardless of polarity. Okay. The second two are only found in polar molecules. You can have dipole-dipole attractions. And the third is hydrogen bonds. I'm going to take, oh, and they also increase in strength as you go down this list. So London dispersion forces are the weakest of the intermolecular forces. Dipole-dipole are a little stronger. Hydrogen bonds are even stronger. Okay. Okay. So the first one we're going to look at is the London dispersion force. And we're going to look at pentane. So it says on the slide N-pentane, and all that means is normal pentane, which means that it's in a chain. So you have a 5-carbon chain. Okay, and it has to interact with another 5-carbon chain. Okay, so in the molecule of pentane, you have only carbon to hydrogen bonds and carbon to carbon bonds. So pentane is nonpolar. Okay. But what can happen is you can have some kind of disturbance. It could be math, it could just be the probability of the event taking place. But the disturbance is going to cause the electrons in the molecule to gather momentarily on one side of the molecule. Okay. So if all of the electrons in pentane suddenly end up on this side is going to be a little bit negative, and this side is going to be a little bit positive. So this buildup of negative charge density is going to affect what happens with the electron distribution in this molecule. So this side will become a little bit positive, and this side will become a little bit negative. When you have opposite charges near one another, they're going to attract, and this is the London dispersion force. Okay. Now, it's sort of like having a domino effect. So molecule A affects molecule B, which would affect molecule C, molecule D, so on and so forth. But without London dispersion forces, every single compound would be a gas. The heavier the compound is, the stronger the London dispersion forces are. Okay. Now, there are constitutional isomers of pentane. So you have the chain version and you have the cross version. Okay. These two, the linear version, these have a greater amount of surface area that can interact. This has lower surface area that can interact. This will have the higher London dispersion force. This will have a lower London dispersion force. Okay. The strength of the attraction gives you information about the energy required for a phase change. The stronger the interaction is, the higher the melting point will be, and the higher the boiling point will be. So this chain version of the compound C5H12 has a higher boiling point than this constitutional isomer of C5H12. Okay, so it's not only weight, but it could also be shape. Okay. Now, these dipoles that end up forming in London dispersion forces are temporary. Eventually, at some point, they're going to go back to their normal distribution. So these are called momentary or temporary dipoles, and they will occur in nonpolar compounds. But if your molecule is always polar, then it can have what's called dipole-dipole attractions. Okay. And these are found in permanently polar molecules. Okay. So the example we're going to use is acetone. So acetone looks like this. Okay. The carbon to carbon bond component is nonpolar. The carbon to hydrogen bond is nonpolar. So this part of the molecule over here is not polar. But the carbon to oxygen bond is always polar in the direction of the oxygen. Okay. So when you have a set of acetone molecules, they're going to line up so that the partially positive end of one molecule will see the partially positive end of the neighboring molecule. So this is partially negative, partially positive. Then there would be an attraction here. Okay. But intermolecular forces are additive. So not only does a molecule like acetone have dipole-dipole attractions, but it also would have London dispersion forces. So everything has London dispersion forces, and only if the molecule is permanently polar do you get dipole-dipole attractions. Okay, the last one is the hydrogen bond. Okay. And hydrogen bonds are a special kind of dipole-dipole attractions. And they require a few structural components. The first component is that the molecule must have a hydrogen, but that hydrogen has to be in a polar bond to a nitrogen atom, an oxygen atom, or a fluorine atom. Nitrogen, oxygen, and fluorine are the most electronegative atoms on the periodic table. And so when hydrogen is bonded to one of those elements, the bond is very polar and the hydrogen is very partially positive. Okay, this molecule that has the hydrogen in the very polar bond has to be next to a molecule that either has a nitrogen, oxygen, or fluorine, or has an element that has lone pairs of electron. Okay. The easiest example is to look at water. So this is molecule A, and it's going to interact with molecule B. Okay. So what you would do is you would recall that water is a bent molecule. Oxygen to hydrogen bonds are polar in the direction of the oxygen atom. So the oxygen is a little bit negative, the hydrogens are a little bit positive. Okay. This oxygen is one of these elements that you have to look for in order to say that this bond is polar enough to participate in hydrogen bonding. Then what you do is you say, is it next to a molecule with nitrogen, oxygen, or fluorine, or lone pairs? And in this case, it has an oxygen which has lone pairs. So now this interaction is strong enough to be called the hydrogen bond. If a molecule is experiencing hydrogen bonds, it also has London dispersion forces, which would be sort of in this same area of the molecule, and it would have London dispersion forces. So they become additive. Okay. Are there any questions at this point, because we're done now with chapter 1 and 2 and we can move on into resonance if there aren't any questions?
I have a quick question about dipole-dipole.
Okay.
I've seen molecules that like have a really long carbon chain. And at the end of the carbon chain, there would be a polar portion, like the hydrogen oxide, or well, that would be hydrogen.
Yeah, like having an alcohol.
Yeah. And you had said that the dipole-dipole molecules have to be, they're permanently polar, but
yes.
like you have what would you call that portion? if it's the whole molecule is actually nonpolar because of the length of the carbon chain, but that one piece is polar.
Okay, so let's draw a couple. So here's ethanol, so a 2-carbon alcohol. 1, 2, oops, too many. 3-carbon alcohol. 1, 2, 3, 4. 4-carbon alcohol, and then let's say we have something crazy like this. Okay. Now you would say that all of these molecules are polar. The presence of the oxygen here, no matter how long this chain is, you would still say this molecule is polar. It's just not as polar as this molecule. So polar or nonpolar isn't yes or no. You actually get a number. It's called the dipole moment, and it's given the symbol mu. Okay. The higher the value of mu, the more polar the molecule is. Okay, so something small like ethanol, which has a small hydrocarbon chain, this will be polar enough, to mix with water well. Something like this that technically is polar but has this huge, as you say, hydrophobic hydrocarbon chain, this one will not mix well with water, but it's still technically polar. It would just have a very small dipole moment. And you could say this portion of the molecule is nonpolar, this portion of the molecule is polar, but overall, you still would have a dipole over here. You can't, there isn't anything over here that will cancel that dipole. Does that make sense? Because they're vectors, they're not scalars. So do you know and it's okay if you don't, do you know the difference between a vector and a scalar? Or do you remember?
Yeah, I took physics last semester.
Okay, so the presence of this vector isn't canceled by the presence of anything else over here. So it's still there, it's just less polar. And this one would be more polar. And what you would see in terms of like dissolving like is the smaller the alcohol is, the more likely it can mix with a polar solvent like water. The less polar, the less likely it will mix well with water. Does that help?
Yeah, thank you.
Okay. All right. Any other questions about chapter 1 and the first part of chapter 2? I'm hoping these representations are getting a little bit easier for you to read. Okay, so we'll start.
Quick question.
Oh, sure. No, it's okay.
So kind of like building on to what she said, what if you have like the polar portion in the middle of the hydrocarbon chain? Does it still produce the same effect?
It's going to be similar. So let's say you had 2 ethers. Okay. 1, 2, 3, 4, 5, 6, 2, 4. Okay. This ether is going to be more polar than this ether. But it's still going, this one will still be polar. It's just going to be less polar. It'll have this one will have the higher dipole moment. This one would have the lower dipole moment. Now, the problem with polarity, like what if you had you could say, well, what if you had a compound that looked like this, that looked symmetric, right? This looks symmetric. So you have a central carbon and you have a carboxylic acid on the left, carboxylic acid on the right. Okay. The problem is all of these bonds can rotate. the single bonds. So even though right now this orientation looks symmetric and you could say, well, maybe they're going to cancel, it could always rotate in such a way that they won't cancel. So for large organic molecules, you're going to have non-polar molecules like these just regular hydrocarbon chains. But as soon as you have a heteroatom on there, it's going to be polar. But it may not be as polar as a different hydrocarbon chain with a heteroatom.
So those will still have the dipole forces, correct?
This one will, yes, and so will this one. And this one will have hydrogen bonds because of this OH component. But all this one can do is participate in London dispersion forces. So bonding is a grayscale. So you have a breakdown that looks like this. So you have 0 to 0.5, oops, that's not right. 0 to 0.5 to 2.0, and then greater than 2.0. So if the difference in electronegativity between two atoms is between 0 and 0.5, it's considered nonpolar. If the difference is between 0.5 and 2, it's considered polar. If it's greater than 2, the bond is considered ionic. Okay. So technically, the carbon to hydrogen bond is right here. So it's kind of borderline. There are people that argue that it is technically polar. But like, what if you had a compound that was right here, right on 0.5? Is it nonpolar covalent or is it polar covalent? Well, you'd have to look at the properties of the compounds. Polar molecules tend to have higher melting points and boiling points than nonpolar molecules. Okay, ionic compound, if you had a compound right here, you say, well, how do you know that it's polar covalent and not ionic? Well, ionic bonds are salts, and those tend to have much, much, much higher melting and boiling points than covalent compounds do. So it's like this is saying there's no tug of war on the electrons in the bond. Polar is saying there's tug of war on the electrons in the bond. Ionic is saying that you just played tug of war with the, what do they call him? The mountain from Game of Thrones, and you ripped your arms off. So ionic bonds, the dipole is so strong that the electrons are transferred. Okay, so this would be like, here are the electrons in the bond shared evenly. Here they're shared unevenly. So A to A to B, A to C. You make ionic. So if you're at these breakpoints, it's hard to tell. But for organic compounds, if you have a symmetric hydrocarbon, that's small. It's going to be nonpolar. Okay, even if the bonds in it are polar. This is carbon tetrachloride, but it's still symmetric. So those bond vectors will cancel. As soon as you have asymmetry, it's polar again. So this is, let me write that in a different color. Nonpolar, nonpolar, polar. Okay, but your compounds, like this kind of stuff, like these kind of hydrocarbons are boring. All you can do with these are burn them. They make very good fuels. And the heavier ones, like methane is a gas at room temperature and pressure because it's so nonpolar, it has such weak London dispersion forces that it remains a gas at room temperature and pressure. As you get closer to like a 5-carbon chain or a 6-carbon chain, then they're liquids and they make very good solvents in reactions because they don't interfere with the reaction. This is nonpolar carbon tetrachloride. You can use it in organic reactions, and this though suddenly becomes polar. And so once you get more carbons involved, then you're going to almost essentially say that unless it's just carbons and hydrogens, it's going to end up polar. But then remember that polarity is a grayscale. So it could be really polar or it could be a little bit polar. And that would be given by that number, the dipole moment. And that's a hard thing. It took me a long time to get that in my head, that it wasn't black and white, that water is polar and it's very polar. Ammonia is polar, but not as polar as water. So it just takes a little bit to kind of get used to considering things that as being a sliding scale. Did that answer your question?
Yeah, thank you.
Okay. Okay, well, we're going to just stop here because I don't want to start a chapter with hardly any minutes left. So this is pretty much now the end of the review of what is general chemistry. Right now, that's important to move on. So look over things over the weekend. If you have questions, feel free to shoot me a text. I mean, quarantine vacations are home a lot. So, but other than that, I will see you on Tuesday and we'll start with resonance. And that shouldn't take the whole time. So hopefully we'll get into chapter 4 too.
Are you going to post the annotated slides?
Yes, I will now. Yes, after this lecture, I'll post all my old annotated slides, and then these videos will be up too.
Awesome, great, thank you.
Yep, no problem. And if you guys want, I mean, there's pluses and minuses to both viewpoints. I can wait till after the chapter is over to post the annotated slides, or I can post them beforehand. It really depends on what you think is going to be the most helpful, because that's the whole point. I want to make sure that you guys have the resources that you need to do well. So if you want them beforehand, I'm happy to load them all today. So if you guys want, if you want to go to participants, if you guys want to just vote and tell me what you think. Yes, you want them beforehand. No, you want them after. I don't want you to stop coming to class. That's the only hesitation of posting them beforehand. So the voting is coming in. It's pretty even. There's only, the other thing would be is if there's anybody that wants, I can always post them and you cannot look at them until afterwards. That could be the easiest way to go. Okay, well, I'll post them then, at least probably not past what will be on the first exam, and then you can start looking through them, and maybe it's just nice to have them available to see what's coming on any one slide or why it's written on there. All right, well, you guys have a good rest of your day and enjoy your long weekend. It looks pretty out right now, so I will see you guys on Tuesday then.
Thank you very much.
Yeah, you're welcome. Have a good weekend.